Assalamu alaikum. In this video, we are going to use a difference equation of a causal, linear, time invariant, discrete time system to determine the transfer function h of z, express this transfer function in a factored form, determine the values of poles and zeros, sketch those poles and zeros, and from the plot we want to determine if the system is stable or not. Okay, so first of all, what is a difference equation? This is a difference equation, and as you can see, it is an equation that represents the relationship between the input and the output. And also, as you can see here, that the output depends on not only the current input, but also previous or past values of the input and past values of the output. So, in summary, a difference equation is an equation that represents the relationship between the input and the output of a given linear time invariant system. Now, what is the transfer function, or how do you find the transfer function? Let me just remind you or tell you that to find the output of a system, what did we used to do? We said we multiply the z transform of the transfer function by what? The z transform of the input. So this is the output. This is transfer function, and this is the input, or the z transform of the input. Now just rearrange to get h of z. H of z is y of z over x of z. Okay? So in the difference equation, we have terms of y equals terms of x, right? What we want to do, and they are in the time domain, what we want to do is here yn x of n. What we want is to get the z transform of both sides, the left hand side and the right hand side, and then after we find the z transform, we want to rearrange to get y, this term, y of z over x of z. Okay, so let's start. What do we have? We have y, wait a second. We have y of n plus 1.5 plus j 1.5, y of n minus 1 plus 0.04. Let's just be neat and do this. Minus j 0.02, y of n minus 2 plus 0.081, y of n minus 3 equals I'm just writing out the difference equation again. 2x of n plus 5x of n minus 1 plus 0.1 x of n minus 2 plus 0.02 x of n minus 3. Another reminder, if you have x of n, the z transform of x of n is x of z. If you have a delayed version of x of n minus d, then the z transform is z to the power minus d x of z. So we are going to use that to find the z transform of both the left-hand side and the right-hand side. So what is the z transform of y of n? It is y of z plus 1.5 plus j 1.5. What is the z transform of yn minus 1? There's a delay of 1, so z minus 1 y of z plus 0.04 minus j 0.02, and then what is the z transform of this? It is z to the power minus 2 y of z plus 0.081 z minus 3 y of z. Okay, and it is equal to, now we're going to take the z transform of the right hand side, and it's 2 x of z plus 5. What is the z transform of the delayed x of n? It's z minus the delay x of z plus 0.1 z minus 2 x of z plus 0.02 z minus 3 x of z. What do you notice here? Each term of the left-hand side has y of z. What can we do in this case? We take y of z as a common factor. So what's left is 1 plus 1.5 plus j 1.5 z minus 1 plus 0.04 minus j 0.02 z minus 2 plus 0.081 z to the power minus 3. This is the left-hand side. What about the right-hand side? Let's see. What is in common here? X of z is in each term. So we take x of z as a common factor. What's left? 2 plus 5z to the power minus 1 plus 0.1 z to the power minus 2 plus 0.02 z to the power minus 3. Now to get this equation to give us the transfer function, we need an expression like this, y of z over x of z. How do we do that? We divide both sides by x of z, and we divide both sides by the expression that is next to y of z. So at the end, when you divide this side by x of z, you lose x of z from here, and you get x of z, y of z divided by x of z, and then you take this whole term and you divide both sides by it. So at the end, you get this. 2 plus 5z minus 1 plus 0.1 z minus 2 plus 0.02 z minus 3 over the term, this term, the brown term, which is 1 plus 1.5 plus j 1.5 z minus 1 plus 0.04 minus j 0.02 z to the power minus 2 plus 0.081 z to the power minus 3. Okay? So this is our transfer function, h of z. Y of z over x of z is h of z. H of z. So generally, h of z is, to generalize this, expressed as two polynomials, a numerator polynomial and a denominator polynomial. And the general form of the numerator polynomial is like this: b0 plus b1 z to the power minus 1 plus b2 z to the power minus 2 plus terms until, let's say, b l z to the power minus l, and the denominator generally expressed as a0 plus a1 z to the power minus 1 plus a2 z to the power minus 2 plus other terms until let's say m z to the power minus m. So, and then this becomes, just for the sake of being complete, let's just express it as a summation from k equals 0 to L bk z to the power minus k over summation from k equals 0 to m ak z to the power minus k. So we found the transfer function. So why am I doing this? Why am I telling you about B's and A's? In MATLAB, when we are dealing with transfer functions, or when we're defining transfer functions and using different commands to manipulate them, when we enter them, we should enter them as vectors. And how do you enter those vectors? You enter two vectors. A vector B, let's stick to our color code. We have a vector B, which will be B0, B1, B2, up to BL, and another vector A, A0, A1, A2, until AM. Okay, so when we're dealing with transfer functions in MATLAB, we are going to give it two vectors, a vector B, which represents the numerator polynomial, and vector A, which represents the denominator polynomial. So in our case here, what is B0? B0 is 2. What is B1? It is 5. B2, 0.1. Finally, B3 is 0.02. What about the A's from here? The first one is 1. The second one is 1.5 plus J 1.5. The third one is 0.04 minus J 0.02. And finally 0.081. Okay? Now we are going to use MATLAB. So in MATLAB, we're going to define the two vectors B equals 2, 5.1, 0.02, and then the vector A, 1 space 1.5 plus 1.5 J. Notice here in MATLAB you have to write J at the end. Space 0.04 minus 0.02 J space 0.081. Okay, now to find the partial fraction, we use a function called residuez. You will you can do doc to Z to know more about the function. I'll let you explore that on your own time, but I'll tell you that this is how you use it. First, you tell MATLAB that you want the output to have the residue, the poles, and C, which is a constant, I'll tell you about it later, equals what? Equals residue Z given B and A. Okay, so it is giving us R's, the residues, the poles, and the term C. So now what does all of this mean, or how can I use this? Let me tell you how you can use this. We have little space here. Let's use it. Okay. So now this is the factored form. So h of z equals, now the constant term will be first here, 0.2469. If you check a book or your lecture notes, this is A0 in the partial fraction expansion, plus, now the first term here will be A1, which is the numerator here. So it's going to be 0.3344 plus J 1.6671 over, this is the pole, so it here in the denominator it will be 1 minus the pole. Okay, so it's 1 minus, what is the expression of the pole? It's minus 1.4933 minus 1.5, here it's J, sorry I'm running out of space, J 1.5020 Z to the power minus 1 plus, again, so this is A1 and then the second term is 0.747 minus 0.822 J here, 0.8221 over 1 minus the pole. What is the pole? It is minus 0.0785 minus J 0.7 1795 times z to the power minus 1. This is A2. And then finally, plus, what is the numerator? Here it's 0.6717 minus 0.8450, and this is j, don't forget, over 1 minus the pole, which is 0.0717 plus j 0.1815, and don't forget c minus 1, and this is A3. Okay. What's next is we need to find what? The zeros and poles, the values of the zeros and poles. Obviously, you can see the poles here, but we use another function. Let me show you. Sorry, my MATLAB stopped working for a while, now it's back. The other function is used this way: zeros, poles, and the gain equals transfer function to 0 pole gain given b and a. So here you're telling it that you want the output to be zeros, poles, and a gain k. When you read the document for transfer function to zeros, poles, and gain, you will know why you need k. But in this case, we don't need k. It's to basically view or write the transfer function in another form, but we are not concerned with that right now. What we want is the values of the zeros and the poles, and this is the values of these are the values of the zeros, and these are the values of the poles. We want to see the plot of the zeros and poles, so we use another command. It's called zplane, and then zplane given b and a. It will give us a plot. This is our plot of the zeros and poles. Here the zeros are represented by O, or the dot, or the empty circle, and the poles are represented with the x's, as you can see. And obviously this is what is this? This is the unit circle. How do I know? The maximum value is 1, so this is the unit circle. So is this filter, or is this system stable or not stable? Basically, because one of the poles is outside the unit circle, then this system is unstable. If all of the poles were inside the unit circle, then we would say that the system is stable, but since one of them is outside the unit circle, then this system, we conclude, is unstable. So to summarize, we had the difference equation. We wanted to get the transfer function. What we did is we got the z transform of the left-hand side and the right-hand side, and then we rearranged for y of z and x of z to get h of z. Let's see it here. H of z is y of z over x of z. So we manipulated the difference equation until we had this expression of y of z over x of z. And then when we got it, we noticed that it's a polynomial in the numerator and in the denominator. And then I told you that in MATLAB, instead of entering the transfer function as a polynomial, what we do is we use vectors, two vectors, b and a vector for the numerator polynomial and a vector for the denominator polynomial. And then we used a function called, or a command called residuez. This is it, residuez, to find the partial fraction expansion of the transfer function, because we were requested to express the transfer function in a factored form. Okay, and then after that we found the values of the zeros and the poles using the TF to zpk function or command. And then at the end we plotted the plot of the poles and zeros using the zplane command. And that's it for now. Thank you for watching.